Hello. So in this, we'll try to go through a character level RNN, and this is a pytoch tutorial. So what they are doing is they are using it for classifying names. What it means that there is a list of. So here I have downloaded the data. So if you go to the data names, there is a list of nationalities or the language and the name with that language, and they will train a character level RNN and try to predict that. So the beauty of neural networks or the RNN is that we don't need to know the internal details. We won't be doing um, any complex algorithms or matching. We'll just use the plain neural network, and we'll train it and it will try to predict. So I think that's the beauty of RNN. So let's start. So here I have so here it's a one plain file, but I have broken it into its own files or modules so that I can uh, import those modules, and then maybe if I have to do any modifications I can do easily. So for example, here if I start from the beginning, they have the preparation of the data, pre-processing. So I've created a processes called processes file. I moved most of this code here, and yeah, and if I go down, uh, so this is where they are creating their RN module. So I have put that here, model pytoch tutorial, so that if you have to change it with someone else, we can do it easily. And then this is our training part, so where we are training and we are evaluating and we are predicting. So I'm using Visual Studio. I have created a content environment, and I have on that we are running this. So let's now run it and see where we are. I've also used TorchWiz to just to try to go into more depth of in more deep how the neural networks work on to get an idea, so that when we try different variations of neural network, we can get an idea how they are behaving. So let's start, I think, and we'll put one of the reasons I want to run it on Visual Studio Code is I can have the breakpoints. I can see what are the values, and if I have to instead of using the print statements on Jupyter Notebook, it will help me in doing more analysis right in the flow in the program. So let's debug and see what's happening. Yeah, so let's now run our module. So we'll run. So first of all, we have. So let's go through what this is creating. So now step in. So let's see what is it's creating. So here if I see what values I have passed, so input size is my 57, input size is all visible ASCII characters. I think it's a that's where I have defined it. So this ASCII characters, so plus these values. So if I go okay, so these are ASCII characters. Actually, these are alphabets. So then I have defined my hidden size, which is 128. So my input size is 57 and my hidden size is 128. Then as they are defined, so I've defined input to hidden layer, which is 57 plus 128, and the output, it's a linear layer, and the hidden size is 128. I'll go more in detail in this. And then I define again the same, it's hidden output plus output size, which is 19. Okay, and then I'm defining a softmax function, and then it just goes out. Okay, so now I have defined a criteria, which is a negative log likelihood loss. We'll again go more detail into how it's working. And let's go down. So I think what we have to do is now we have to train it, and so train is basically you have to run this fit function. That's what we have defined it here. And we will, what we'll also do is we'll save this RNN model in some file, so that we can then run evaluate on top of that, so that we don't have to run this file again and again. So let's go. Now it will run the fit function. So let's put points in that. So we'll run it for 100k times. Every 5k it will print, and every 1k it will plot. Every 100k, every 1k. So this is my current loss, and this is the area of all losses. We'll start the time, and now let's go into this. So we'll first okay, I put it breakpoints here. So it will pick a random category and random line. Category tensor is the output tensor. So here the category is Spanish, and my all category Spanish is 18. So it will contain the value. It should contain the value 18. One tensor. The line is from that it has picked a random from Spanish for its put Oreo. So it should be a len tensor of 1 2 3 4 1 2 3 4 5 5. Size should be 5 1, and for each 5 1, and it's one hot encoder. So there will be one out of 57 for each uh, 57 column, we can say. There will be one value which will be 1, and rest will be 0. So you can see that if we just print. So here if we go to output, if we go to console and debug console, and if we see line tensor dot size shape you see it's 1 1 at the position of capital O, because it's a Oriole. Okay. So let's go back. It has returned this category line category tensor, which is dark, which is actually an output tensor, and input tensor. Now it will go, it will return an output loss, and it will do the training mapping, and that is that is where main activity is happening. So I think let's go into that. Yeah, so here we are going creating a hidden yeah. So here, because we have to pass hidden layer every time, we are creating it ourselves. So here we create, initialize it 0, and its size is 128. We have to do this to clean up. Let's see why we have to do 0 CAD. So okay, we'll go more details in that as well, like why we have to do 0 CAD in initially at every time we have to do, because if we don't do the gradients will get add on, and will have a bug in our, will get not bug, will get we won't get the right answer. So I think every time we are doing backward, it should be followed by 0 CAD. So now let's go. So now so here we'll so what we are doing is we are taking one character one by one and passing it to RN model one by one. So for example, if we run this, so it's giving 0 to 5, and so it's first picking 0. So here we pass, if we see what is this value, line tensor. Yeah, so interesting thing is this is what we are passing to the model, or the input is this value, which is 1, which is O, capital O, nothing, and then we are passing the hidden layer, and we're passing the hidden, which is right now all zeros, and then let's see what it is doing. So let's go more into this. Yeah, so here what we are doing is we are concatenating the input and the hidden. The reason is because the way RNN works, we'll see more in detail. So what we can do is we can combine the hidden input layer and have the one combined weight matrix. So here we are using the cat. So here's the toss.cat. What it does is, given at that particular dimension, it will concatenate both matrices, and so the dimension should be same of the dimension of both the matrices should be same, except on the one where we are doing the concatenation, because let's say if the input size is 2, so let's say if we have 2 examples, say here I have 2 examples, x which is of shape 3 2 2, y which is of the shape 2 2 2. So here if I do the concatenation of on dimension 1, it won't work, because it won't be able to concatenate these two values. It won't be able to concatenate on dimension 0, because the dimension, or because the shape is not size. But if I do at dimension 1, dimension 0, it will, because at the end it has to merge, it has to concatenate rest of the values, which is 2 2 and 2 2, it will become 5 2 2. So but the problem is, let's say if I do dimension at dimension 1, it will become 4, but here there is a mismatch. So for example, let's say if I do toss dot concatenate, this will work, but if I do it this way, it will throw an error that the size should match except in the dimension where you are doing the concatenate. So let's move ahead. So this is our combined one, and so if I see combined shape, it's 1 and 185. Then let's go back down, and then what now we are doing is we are running this through the first linear layer. So what is my hidden? Yeah, so let's see what's happening in this is, so what it does is, so it just, so let's say if we go and see what the nn dot linear does. So what it does is calculates x a transpose plus b. So what is a is? A is the weights of the hidden layer, or weights of the linear layer, and b is the bias. So let's see what's happening here. So what we have done is we did some calculation where so this is the weight of I to H layer. This is the shape. If you see that the shape is in the reverse direction, which is the output and then the input. So we have to take the transpose to before we multiply it with the input, as our input is 1 cross 185, and the bias is again related to the output layers, which is 128. So if we manually calculate is, what we are doing manually here is, we are, so combined is our input. So here what we are doing is we are doing the matrix multiplication with the weights of, we are first getting the weights of the I to H layer, and then doing the transpose, and we are doing the matrix multiplication, and then we are adding the bias. So we got this layer Y, and if we run, if we and if we do the equality check, using torch equality check, it will compare each element of A with B, and it will return a true or false, and with all it will return that if all values are true or are equal. So if I run it, it's showing me true. So what it is doing essentially is it's just calculating the matrix multiplication on the first layer, and the same we are doing with the output. So what output is doing is, output is again doing the same thing. As we have 2-layer network, it is taking the combined one, which is again, it's not taking the hidden layer output, it's taking the input layer, and it's creating the output. So it's again the same thing, and then we are running the softmax from the output, but output will be, it won't be 128 layers, it will be, if I do the size of shape of output, it's 19 characters, 19 length, and we are running the softmax to get the probabilities. If I do the output right now, and then if I do the softmax, so it has run a softmax, will do a we'll go more detail into what it is doing, how the values are changing. If we see, it will be making, it has actually made all values negative. So I'll go in more details into what the log softmax is doing, and then it's returning the two values, the output and the hidden. So one thing important is in the first iteration, if we are saying that the output is not related to hidden as of now, because we ran the same operation on the hidden and the output, and we just ran an extra step which is softmax on the hid or on output, and then we are returning it back. So let's go back. So here we are creating the torch vision just to see how, what it does is it creates a autograd will. Yes, if we see what is torch which is doing is torch which creates a visualization for the execution graph, so that we can understand how the backpropagation will work once we run the backward function.